Hello, welcome to another module in this massive open online course. In this module, let us start looking at another important concept in linear algebra and also pertaining to the solution of system of linear equations, and that is the least norm solution. So far we have seen the least square solution. We will now start exploring the least norm solution. Okay. So, what we want to do is essentially we want to look at the least norm solution. So, this is the least norm. Previously we have looked at the least squares. Now we want to look at the least norm solution. Okay. So, once again consider the system of linear equations we have y1, y2, ym. This is equal to once again the matrix A comprising of the columns A1 bar, A2 bar, so on up to AN bar times the vector x bar, which is x1, x2 up to xn plus, that's it. This is the system of linear equations. Except in this case, so we have this matrix, this is an m cross n, and for the least norm problem specifically we have m less than n. So, we have m cross n matrix, m is the number of equations, n is the number of unknowns, and we have m less than n, right. So, this system of linear equations is essentially characterized by the fact that number of equations, so m less than n, this implies that number of equations is less than number of equations is less than number of unknowns. Okay. So, the number of equations is less than the number of unknowns. Also m less than n, remember m equal to number of rows of the matrix A. So, you have this is basically your matrix y bar, this is basically your matrix A, and this is your matrix x bar. So, you have y bar equals A times x bar. So, you have the matrix A, n equals number of columns, right, of A of the matrix A. So, if you look at the matrix A, that looks like, so this is your matrix A, this is the number of rows, and this is the number of columns. So, number of rows is less than the number of columns. This implies m less than m implies that the height of the matrix, if you look at the number of rows as the height, so the height of the matrix is less than the width, implies this is a wide, right, implies this is what is known as a wide matrix. So, if you look at if you want to find a form picture of the system in your mind, it is always useful to form a mental picture in your mind. So, we have an underdetermined system of linear equations. So, to form a mental picture, essentially you have a matrix A in which the number of rows is less than the number of columns, that is the width, that is the height is less than the width, which implies this looks like a wide matrix essentially. Remember, the least squares was the other way around. The least squares had number of equations more than the number of unknowns, right. So, number of rows was more than the number of columns, over determined system of matrix, over determined system of linear equations, and therefore, the corresponding matrix looks like a tall matrix, all right. So, the least norm, so the wide matrix is for the least norm, and the tall matrix, if you look at it, right, in which you have the number of rows and this you have the number of columns, in which m less than n, this is for the least this is for your least squares, right. So, just remember, it is useful to remember that least squares is usually associated with a tall matrix, least norm is associated with a wide matrix. Okay. Now, so coming back to our least norm, what you can see is now you have y1, y2, ym equals your matrix A, A1 bar, A2 bar, An bar, x1, x2, now basically if you look at the rank of this matrix, rank A, if you look at the rank of this matrix, which is less than or equal to the minimum of m comma n, number of rows comma number of columns, which now m, given m less than n, this implies this is less than or equal to m, right, since we have m less than n. So, rank is less than or equal to m, which implies the rank of A is less than n, right, which essentially implies that rank of A is less than the number of columns, right. So, implies the columns are linearly dependent or not, implies the columns are linearly dependent. That is, there exists a vector u bar such that A times u bar equal to 0. That is, u bar such that A times u bar is 0, and in fact we said, we defined such a vector u bar. This u bar belongs to the null space, this u bar belongs to the null space of A, right. So, this is basically your null space of u bar belongs to the null space of the matrix A, which means that this wide matrix essentially has a non-trivial null space, right. So, for instance, if you have a single vector u bar which belongs to the null space, then any multiple of u bar, that is k times u bar, also belongs to the null space, and so on and so forth, and then you will have a basis for the null space, and so on and so forth. So, the bottom line here is that if you look at any solution, let us say you have A x bar equal to y bar, A x bar equal to y bar, which is a solution. So, let us say x bar satisfies this. So, x bar is a solution. If x bar satisfies this, implies any A x bar plus u bar is equal to A x bar plus A u bar. So, u bar belongs to the null space of A. Now, A u bar is 0. So, this is equal to A x bar, which is equal to y bar, and therefore, this implies that if x bar is a solution, then any A x bar, then any x bar plus u bar is also a solution, then any Ax, then any x bar plus u bar is also a solution, implies there are infinite number of solutions, there are infinite solutions to A x bar equal to b bar. The number of solutions to this system is infinity, right. So, in fact, if you compare it once again with the least squares, when you have a tall matrix, the problem there is that there is typically no solution. The solution exists only if y bar lies in the column space of the matrix A, right. So, in the overdetermined case, there is no solution. In the underdetermined case, typically there is an infinite number of solution. Of course, once again we have to clarify, there is a slight caveat, if A has full row rank, that is, if the rank, that is, for any vector A, this will have an infinite number of solutions. I will just qualify this, there are infinite solutions. The qualification here is if, once again, rank of A is equal to m, that is, rank of A equal to m, meaning that is implies A has full row rank. If rank of A is m, implies A has full row rank. In that situation, this has infinite number of solutions, which means now we have to constrain the solution. So, we want to find a particular solution. Now, typically, given the infinite number of solutions, how do we isolate the best solution? One of the ways to isolate the best solutions, typically, especially in machine learning, signal processing, it is usually seen that the best solution among these infinite number of the solution is one that has the minimum energy. So, we want to find the minimum energy solution right, find the minimum energy solution, right, implies minimize. Remember we said the minimum, if you represent a signal by a vector, then the minimum is the energy is given by the norm. So, we minimize norm x bar, which again is similar to minimizing norm of x bar square, because remember if you are minimizing norm of x bar, that is equivalent to minimizing the norm of x bar square, and this we are doing in order to in order to constrain the solution, right. What do we mean by that? Because there is an infinite number of solutions, so you cannot determine a unique solution. Therefore, we have to impose additional constraints. One of the logical constraints that we are saying, and practically useful constraint, is to determine the signal or the classifier, right, which has the minimum energy, and essentially that is what we are trying to do over here, minimize the norm, find the solution x bar which has the minimum norm. And therefore, this problem can be formulated as, therefore, this problem can be formulated as minimize the norm of x bar subject to the constraint x bar equal to b bar, right. So, what we mean by this is, among all the solutions, find the one that has the minimum energy or the minimum norm or the least norm. Therefore, this is known as the least norm solution. Remember previously we had the least square solution, now we have the least norm solution. So, among all the solutions, find then the one that has least norm. This is the least norm solution, right. Among the infinite number of solutions, find the one that has the least norm. That is why this is the least norm problem. And remember, you can also equivalently formulate this as minimize norm of x bar square, right, minimize norm of x bar square. Once again, this can be solved using the Lagrangian convex. So, this is a convex problem, this can be solved using the Lagrangian cost function. Except here you realize that you have a x bar equal to b bar, which means A is m cross n, there are m equations, implies that there are m equations, implies there are m constraints. And therefore, we need m Lagrange. Some of you might be familiar with this theory, which implies that you need m which implies that you will have the vector lambda 1, lambda 2, lambda n this is equal to lambda bar. This is the vector of Lagrange multipliers, right. So, we can say this is the vector of Lagrange multipliers because you have m constraints. So, this is the vector of Lagrange multipliers. This is the vector of Lagrange multipliers, and therefore, you can formulate the Lagrangian for this as f of x bar comma lambda bar, that will be minimize norm of x bar square plus the Lagrange multiplier vector lambda bar transpose times y bar minus a x bar. Norm of x bar square, I can write this as x bar transpose x bar plus I can write this as y bar minus a x bar transpose lambda bar, right. A transpose b bar equal to b transpose a bar, which I can write as x bar transpose x bar plus y bar transpose lambda bar minus x bar transpose a transpose lambda bar. Now, again from the optimization theory, right. From optimization theory, at optimum we must have the gradient with respect to x bar, this must vanish. Now, taking the gradient, we have already seen that gradient of, what is the gradient again? You might recall the gradient is nothing but the vector of partial derivatives. Take the derivative of f with respect to each component of x, right. So, this implies that x bar transpose x bar, the derivative is twice x bar plus y bar transpose lambda bar, derivative with respect to x bar is 0 minus x bar transpose a lambda x bar transpose a transpose lambda bar, derivative with respect to x bar is a transpose lambda bar equal to 0, which essentially implies that x bar equal to half a transpose lambda bar. This is the property of the optimal solution, least norm solution, and you can see a very interesting property. Optimal x bar lies in the column space of A transpose, right. This is a very interesting property, the optimal x bar equal to A transpose lambda bar. This shows that the optimal x bar has to lie in the column space of A transpose, right. So, x bar equal to half A transpose lambda bar implies the least norm solution has to lie in column space. The least norm solution has to lie in the column space of A transpose. This is the interesting solution, column space of A transpose. And now, substitute this property in the constraint. We have y bar equals A x bar equals A times half A transpose lambda bar. This implies lambda bar equals twice A transpose inverse y bar, which is possible if A transpose is invertible which once again is possible if A is full row rank. Remember, for the least squares, A transpose A is invertible if A is full column rank. Here A transpose is invertible if A is full row rank, that is rank of A equal to M, right, implies rank A equal to M. Okay. And now substituting this, so we have these two properties. So, we have lambda bar equals twice A transpose inverse y bar, and we have x bar equal to half A transpose lambda bar. Now, substituting the expression for lambda bar, this implies x bar equal to half A transpose, substitute for lambda bar, twice A transpose inverse y bar, which is essentially equal to A transpose inverse y bar. This is your least norm, alright, and we can call this as x bar of LS. This is basically what we call as the least, let me just emphasize this, this is your least, one of the counterpart of the least squares for underdetermined, and this is the least norm. Both these again have several applications, and these are very useful to remember, the least squares and least norm, and you can see they are very related, least squares for overdetermined, least norm for underdetermined, alright, and this is given by A transpose inverse y bar if A has full row rank. Once again, you can see the interesting property, which is if you look at this matrix, right, if you look at this matrix, A transpose inverse, then if you multiply this on the right with A, this is equal to A transpose into A transpose inverse, is equal to identity, which means A transpose inverse acts as right inverse of A, and this is termed as the pseudo inverse. We have seen the concept of pseudo inverse, but earlier we had seen the concept of pseudo inverse for a tall matrix, that is given by A, times A transpose A inverse, and you multiply it on the left. Now, for a wide matrix, the pseudo inverse is A transpose inverse, and this is basically a right inverse, right. So, this is a right inverse. So, in the wide case of a wide matrix, this is the pseudo inverse is given by A transpose inverse, right, and this is basically a right inverse, all right. So, this is pseudo inverse of A for a wide matrix, all right. It is important to qualify, because you might see two definitions of the pseudo inverse and might get confused. There is no need to get confused. The earlier definition was for a tall matrix, this is for a wide matrix. And the other interesting thing is A square. If A square is invertible, left inverse, right inverse, both reduce to the same, that is A inverse, and therefore you will have A inverse A equal to A inverse equal to identity. Alright, so for a square matrix, both these reduce to the same, which is again A inverse, and that is also not very difficult to see. Okay. So, this is the least norm solution, and this is essentially the right inverse. So, this is again another very interesting and has several applications. So, you have the least norm solution, it is the analog, as I already told you, the analog of the least square solution for a underdetermined system of equations. All right. So, useful also good to remember that this is for an underdetermined. underdetermined system, that is m less than n. Because once again remember that this is because you have an infinite number of solutions and therefore you want to constrain the system. Okay. Let us look at a quick example. Once again, quick example, always useful to do examples. So, let us have a quick example, y1 y2 equals 1 1 1 1, our favorite matrix 1 2 3 4, and then you have x1 x2 x3 x4. So, this is your matrix A. You can clearly see A is 2 cross 4, m equal to 2, n equal to 4, m less than n, which implies this is an underdetermined solution. Therefore, one can again find the least norm solution. The least norm solution is given as A transpose inverse y bar. Let us ask the question, what is A transpose inverse? Let us find first A transpose. So, that will be 1 1 1 1 1 2 3 4 times 1 1 1 1 1 2 3 4, which if you look at this is given by this matrix. This will be 4, this will be 30, this will be 4, the cross elements will be 4 plus 3 7 plus 2 9 plus 1 10, and A transpose inverse equals 1 over 120 minus 100 equals 20 times 30 4 minus 10 minus 10, and once again if you calculate the pseudo inverse, that is A transpose inverse, which is 1 1 1 1 1 2 3 4 times 1 over 20 into the matrix 30 minus 10 4. You can evaluate this. Again, this will be equal to 1 half 0 minus half minus 3 by 10 1 by 10 1 by 10 3 by 10. Okay, minus 3 by 10 minus 1 by 10 1 by 10. So, this will be 1 half 0 minus half minus 3 by 10 minus 1 by 10 1 by 10 3 by 10, and therefore, the least norm solution is given as x bar least norm. Sorry, I think I have been writing LS everywhere. I think this has to be x bar least norm, right. So, this is your x bar least norm, x bar ln. X bar ls, you can think of it as the least square solution. This is your x bar ln, that is the least norm solution. Okay. So, I think that makes sense. So, x bar ln equals the least norm solution equals this matrix, that is your A transpose inverse y bar, which is 1 half 0 minus half minus 3 by 10 minus 1 by 10 1 by 10 3 by 10 times y1 y2. So, this will be equal to, well, y1 times the first column of this matrix 1 half 0 minus half plus y2 times minus 3 by 10 minus 1 by 10 1 by 10 3 by 10, and this is your least norm solution to the given system of equation. All right. So, this is basically the your least norm solution. All right. So, this is the principle of least norm solution, this is the theory of least norm solution, and as I told you, this is again another very important concept of linear algebra. Least squares, least norm, sort of two sides of the same coin. All right, and this together constitute now the complete set of possible solution for a linear system of equations. So, linear system of equations, m equal to n, number of equations is the number of unknowns. If A is invertible, then you have a unique solution, x bar equal to A inverse y bar. If m is greater than n, number of equations greater than n number of unknowns, then you have an overdetermined system of equations in which you use the least squares, and if you have m less than n, which is now the case that we have seen now, you have an underdetermined system of equations in which we use the least norm. All right. So, those together, this constitute the complete spectrum of solutions for the linear system of equations. Of course, there are minor cases where you can have things such as, for instance, A not being full column rank, A not being full row rank, and then in that case you will have to the solution becomes a little more tricky, but those are special cases, what I would like to call as pathological cases. But by and large, this the unique solution given by the inverse, least squares, least norm, these constitute the complete spectrum of solutions to a linear system of equation, all right, by and large. And these are important to know because these arise very, very frequently in practice, and these are again the one of the most significant applications of the principles or concepts of linear algebra that we have learned. All right. So, let us stop here and we will continue in the subsequent modules. Thank you very much.